Afternoon, folks. Thanks for coming to our talk. My name is Jagain Sundar, and this is Brett Rudenstein. We work for Vandisco. And today's topic is eventually consistent systems versus strongly consistent systems in big data. It's a bit of an arcane topic, and I'm happy to see all of you folks here. So let's start with defining eventually consistent systems. We're talking about distributed systems here and systems that want to keep multiple replicas of the same data, the same state machine. The eventually consistent systems will allow you to have different data in the different replicas for some period of time till what is known as an anti-entropy process is run to make all three systems or all five systems consistent again. If you go back to your college years, entropy in the world of physics means randomness or thermal randomness, which is an indication of the nature of the data. You've really got random data in your three replicas or five replicas. If you run the anti-entropy process, there are some determinants that are used to make one of those replicas be the correct one. The thing that people miss often is that these systems are in an inconsistent state for large periods of time. So if you take 1,000 milliseconds, if you run your anti-entropy process every 1 second, it may be that for 950 milliseconds you're inconsistent and you're consistent for just 50 milliseconds, which is something that the eventual consistency systems will try to fix using various workarounds, such as trying to get it consistent before reads, trying to get it consistent before writes are acknowledged. But the net result is really that you're going to get eventually, we're going to get a large number of inconsistent answers to your queries. The distinction between this and a strongly consistent system is that coordination is not done before changes are made. We'll come back to this concept several times during the course of this presentation, but the important thing is that if you want a consistent replicated system, you have to coordinate before any changes are made to the system. In contrast to eventually consistent systems, Paxos-based strongly consistent systems will keep the replicas always in a same state. If you read a particular cell, or if you read a file, or you list the contents of a directory in a strongly consistent system, you'll get the same response from all of your replicas. This is because changes to that underlying state machine are coordinated using an algorithm. There are many algorithms. The one that I'm particularly interested in today is Paxos, but you coordinate the changes before they're made to the system, and every replica applies the same changes in the same sequence, so you always get consistent replies if you query the system. The result of this is that conflicting changes are never made to the underlying database or metadata system or name node or wherever the state machine is stored. So you will never get two different responses to the same query. There are some very obvious pitfalls to an eventually consistent system. If you are looking at a file system or an object store, new files that were added may not be visible to all the clients. That's a very obvious problem. Appended data, you use a HDFS-like system. If you were to open a file and append some data to it, one replica may tell you that it's 2 gigabytes and another replica may tell you that it's 4 gigabytes. That's a symptom of not consistent replicas. Newly inserted rows in a Hive-like database or some similar SQL interface might also not be visible to some of the replicas. Once in a while, and it depends on various configuration parameters, you'd end up doing an anti-entropy function, and the conflicting changes are discovered and fixed. The anti-entropy change is sometimes as simple as picking the newest write and calling that the current version of that particular cell. The problem with that, of course, you need to have very strong time coordination across all these nodes, and there are significant difficulties with that. Here's a more pictorial depiction of the same thing. If you have a client 1 that's talking to a load balancer which has a series of sharded storage behind it, this is an extremely simplified version of what could be cloud storage. You may find that writes by client 1 are not necessarily seen by client 2. And more significantly, you can have clients 1 and 2 perform conflicting changes. For example, one client may say make dir /a and another client may say create file /a. Both will get success and will happily proceed forward till the anti-entropy function is performed. At that point, you have a problem. You've got to either make one of those win, or you've got to ask for manual intervention before you resolve that conflict. Amazon S3 is probably the most successful and most well-known eventually consistent system. It has a number of quirks that are an inherent part of what the system is. It's a cloud-based storage system, and the specific use or application that I'm going to talk about today is MapReduce from Elastic MapReduce running on top of the cloud-based storage system. The way it works is basically this. You can have objects stored in your eventually consistent storage system, and once in a while when you need to do compute, you spin up virtual machines and have those VMs talk to the cloud storage. When they're done with their compute, the VMs can be shut down or other processing can happen on the same VMs. There is storage on each of those virtual machines, but that's not persistent. When the VM is shut down or the instance terminated in Amazon terminology, that storage goes away. So if you need persistence, you really need to put that data in S3, and therein lies the problem. Here's a pictorial depiction of that. You have S3 storage with its series of load balancers. You have some instance storage, which is the cylindrical things inside the VM box. It turned out that the first few iterations of Elastic MapReduce running on Amazon S3 were problematic. The problem was that MapReduce tasks would run, they would write to S3, but subsequent tasks could not see those results. And if you had an ETL workflow that depended on a series of MapReduce jobs, either written as pig scripts or whatever, you'd find that your first step would work, it would produce results, it would go away, but step 2 would start, it would not find the results because it may be talking to a different load balancer. The example I have here is virtual machines 1 and 2 spin up the mappers and reducers for the first step of a pig script. It writes to S3, it goes away. Step 2 runs in VM3, which is another mapper. It's talking to a different load balancer. And guess what? Because this is an eventually consistent system, the results from step 1 are not visible to step 2. That job will fail, and your ETL workflow will need to be rerun after this anti-entropy step has been completed. Amazon is particularly dense about what they do for anti-entropy, so really retry the job after some time is the answer. So what did Amazon do to make their EMR more usable? They built a consistent metadata layer that's layered on top of S3. This is where problems start, right? I mean, you're talking about S3, which was designed as an eventual consistency system because of performance problems, but now you've got a consistent storage layer or a metadata storage layer built with a traditional database that is meant to resolve that. So you're obviously trading some consistency for performance. So now, in this picture, you can see the external DB. So if you start up an EMR cluster, hidden away is a metadata database that actually holds consistent views of the file changes and the object changes that are made to the S3 storage. So if you go back to the example I talked about, when you run step 2, the MapReduce job in step 2 will talk to this consistent layer and know that there is some object that was created by step 1. You can have a correct ETL workflow. So the moral of the story is that you really cannot build reliable big data workflows if you use a full eventual consistency system. You need strong, consistent replication in order to make a workflow work reliably. The alternative to eventual consistent systems is this algorithm called Paxos. And the important tenet of this algorithm is that you must coordinate changes that need to be made before you make the changes, and all replicas apply the same changes in the same sequence. It's almost as if you give the replicas a set of changes that need to be made, and they go ahead and make that in a very specific sequence. The algorithm that's in use to make up the sequence of operations is called the Paxos algorithm. A little bit about our company. WANDisco stands for Wide Area Network Distributed Computing, and our core intellectual property was developed by our chief scientist who quit his job and sat in his garage and developed a version of Paxos that's time independent, that does not depend on the distance between servers or data centers. It's completely insensitive to latency, and what we have is the ability to run active replicated big data systems across large distances. It's mathematically proven. Paxos is, in fact, the only algorithm that has mathematical proof. This is in contrast with ZAB and Raft and other protocols. By ensuring that you're making changes before applying it, by coordinating before applying changes to the system, you can have active systems. We do not build active read-only standby systems at all. There's no restriction on distance. Again, it's not a SAN block device-based replication technology as you might think. Paxos is this really interesting algorithm that solves consensus among a network of unreliable systems, processes, networks. Consensus really refers to 2 or 3 replicas agreeing on something, and the agreement must be achieved regardless of network failures, processes stopping, coming back, things of that nature. Let me give you a quick overview of how Paxos works, how Decone works, and then I'll hand over to Brett, who's going to do a live demo of our strongly consistent replicated solution for big data. We have a majority quorum. There's a fixed number of participants, and a majority must agree for a change. We have 3 servers, A, B, and C here. They've processed a number of transactions. Let's say we're at 168, 169. By transaction, I mean it could be as simple as a file being created on a file system or data being appended to a HDFS file system. A client connects to server B and says, I want to create file. That becomes a proposal. Remember, no change has been made to the 3 systems yet. All 3 of them agree to that proposal, and it turns into an agreement. It is only at this point that a change is made to the underlying system. In an eventual consistent system, the change would have been made first. If they can communicate with the other servers after change has been made, then the others will follow along. But if there's a network partition, parts of the system will have no knowledge of transaction 170. Let's take a look at what happens when A goes down. We still have a majority, B and C, up and running. They gain quorum, and they proceed with transactions 171, 172, 173. If A comes back because it was a network failure for a moment in time, it looks at it and goes, I've fallen behind. And it's going to grab the transactions from B and C. It's going to apply 171, 172, 173. Only when it's caught up, it's going to start accepting requests from clients to make changes. Again, this ensures that clients do not see outdated versions of the state machine. If there's a complete loss of a replica, you can restore from a snapshot and then apply changes since the snapshot. That's a quick way of bringing up a total lost system. So the application of this strongly consistent replication mechanism is what we call WANDisco Fusion. It's a replication solution for Hadoop that can take parts of your HDFS file system. Let's say you have /hive, /warehouse, /weblogs, which is a database where you store your weblog information. You can replicate that between 2 different Hadoops in a strongly consistent fashion. You can write into that Hive database from both locations. The locations can be running different versions of distributions, and there are some other interesting aspects. In this example, I have 3 data centers. One could be running CDH, one could be running HTTP, and another one, Apache Hadoop. You can be replicating /web logs between DCs 1 and 2, and usage again Hive between DCs 2 and 3. They use different distributed state machines. By that, I mean the Paxos algorithm is run independently for these 2 different replicated folders. That's important because a downtime in DC1 will not impact the replication or the availability of usage again Hive, which is replicated across DCs 2 and 3. We have active-active ingest across multiple data centers, so you can be writing to the same Hive database from 2 different data centers. This is independent of application, so I talk about Hive a lot, but we're compatible with almost all Apache Hadoop applications, Spark SQL, Spark Streaming, whatnot. You can migrate from distro to distro using this capability because one data center can be running an older version and a second data center can be running a new version. We're doing strongly consistent replication, so there is no question of any different data ending up on your 2 data centers. We are also doing continuous synchronization, so if you should lose one data center, you have a modulo whatever WAN speed you could not replicate, you have the rest of your data available in your backup data center. So we are the only active-active replication solution for Hadoop that is in fact an attribute of strongly consistent replication using Paxos. Every other algorithm out there will end up doing an eventually consistent system which can be active in one data center and one data center only. All the other backups have to be read-only. So it's a simple installation. You drop our RPMs or our parcels into your CDH and your HTTP clusters. You have a server running the Fusion server. You can have multiple of those for redundancy and for high availability. And you can declare replicated folders using our user interface, which Brett will demonstrate in just a bit. And strong, consistent replication is going to happen. There's no question of losing data or having different views in different data centers. So with that, let me hand over to Brett for a live demo.
Thought this microphone was going to be in the same data center as my laptop, but so I'm going to do a live demonstration of Fusion across a set of live Hadoop clusters. These are real clusters running up in the Amazon EC2 framework, although we do support on-premise to on-cloud to on-cloud, on-premise to on-premise, doesn't really matter. And in this particular case, I'm running a Cloudera cluster. This is running CDH 5.3, although of course we support all the latest versions as well. It's running up in Amazon EC2 East, so this is running in the Northern Virginia data centers. And I am replicating this data to an Ambari or a Hortonworks cluster being managed by Ambari over in EC2 West. So this is running inside of an Oregon-based data center. So there is 3,000 miles apart. And the demonstration that I'll do is I'll show you how we actually create the replication, how we tell certain folders inside the namespace that they need to be consistent, and then we'll take a look at how users interact with that and how we actually have an audit trail of exactly what goes on inside the system. So for industries that are regulated, financial, healthcare, pharmaceutical, et cetera, they have an audit trail of exactly what the state of the system is at any given point in time. So once you've got your clusters, once you install WANdisco Fusion, you see there's a WANdisco Fusion client down here. This basically gets distributed through the standard services mechanism, the stack and services mechanism in Ambari, installed as a parcel in Cloudera, so very simple setup. Then the question becomes, how do I then manage the folders that I want to replicate? We have the Fusion UI. And when you log into the Fusion UI, the first place that you're brought to is the dashboard. Now the dashboard is showing us a very simple picture right now because everything is in good standing. And it's basically telling you that all memberships have quorum, which again talked about our distributed coordination engine, we talked about Decone. Each of the memberships are fully operational, and the number that you see in each one of these boxes, you see there's a number 2 in the circle here, indicating that there are 2 Fusion servers in the Oregon data center and 1 Fusion server in the North Virginia. These are the machines that handle the synchronous replication of metadata, but to provide LAN speed performance despite having WAN separation, great, in this case, 3,000 miles of distance between these two data centers. What we do is we do synchronous replication of the underlying namespace metadata and asynchronous replication of the actual HDFS file data. That way, we can provide the strong consistency. Another user can't come in and try and write to the same file at the same time, but still have land speed ingest, land speed write at the local data center where you're performing the work. And by the way, as a sort of a side note, what you might have in a production level data center is you might have 3 Fusion nodes in each location so that you have continuous availability of the Fusion service despite things like compute failure, CPU failure, and so forth. So now that you've kind of taken a look at the globe here, let's take a look at how we manage the replicated folders. In this particular case, you see I have 2 folders here that I'm actually replicating despite I have a much larger file system. I've got a folder here called REPL1. It's targeted between my North Virginia and my Oregon data centers. Now, if I had 4 or 5 or 7 clusters, I could target 1, 3, and 5, or 1, 7, and 2. Or any number of clusters in between. So you can decide which data might be able to go within another data center in country, or which data centers can actually replicate outside the country, which folders are. We also see that the REPL1 folder is consistent. It's strongly consistent between the two, but we see this kind of strange behavior in the REPL3 folder telling you that it's inconsistent. Now, the reason that a folder would be inconsistent in a strongly consistent system is, I don't know why. No, actually, there is a real good reason, and that's because normally it has been previously replicated by one of the out-of-the-box tools like a DiskCP, where one data center is typically several hours in front of another data center. So when you first apply replication to a folder, you need to get it into a consistent state. And so if you click on this list of inconsistencies, it'll tell you which files in the data center are actually not the same. In other words, it could be different file sizes, different permissions, different ownership. In this case, it exists in North Virginia but doesn't exist in Oregon. You can resolve that by picking a source of truth and hitting resolve, or because this is the case that I talked about before, we can do a bulk resolve. Choose a data center as the source of truth and click on resolve recursively. Now, interestingly enough, once we go ahead and we start resolving these inconsistencies, when I recheck the file system and it comes back, this will be strongly consistent. In every operation from this point forward will be done active-active, regardless of which data center I actually enter data in. So this was simply resolving a basic inconsistency in a new setup, and now we'll continue on. Also, if I wanted to create a new folder from scratch, I could just hit create. This will bring up the HDFS file tree. I can choose one of the folders in the file tree or one of the subfolders, user, hive, warehouse, or something of that nature. Again, select my target zones. We also choose something about a membership, which is, for the purposes of this discussion, how we sort of tune the quorum engine. So I'll go ahead and click on create there. So you can see that our folders are now completely consistent. So what you've seen is a way right now of managing just those folders that are going to replicate between 2 different locations. Now, what about user interaction? Well, interestingly enough, from a user perspective, it's somewhat invisible. They don't necessarily know that Fusion's running under the covers and that we're maintaining this consistency. So this might be hard. I was looking at the resolution of this screen to, to see, but and the windows up above, and I suppose with the text that scrolls isn't too interesting. This top window is open in the North Virginia data center. The second window down is open in the Oregon data center. And what I'm going to do is I'm going to do bidirectional ingest. I'm going to ingest into both locations at the same time, and I'll show you how that file data gets automatically transferred. So in data center 1, I'll run a basic MapReduce job. I'm going to run TeraGen for about 200 megabytes, just put a bunch of information into the file system. And in Data Center 2, I'm just going to run a basic ingest of some files. This will essentially be the equivalent of doing a copy from local over and over and over, one file at a time, just so I can kind of slow things down. And you can see I've got some activity going on between the 2 file systems. The next thing I'm going to do, though, is what happens if we create a network partition? What if the network went out for some period of time? So to simulate that, in the last window, as you see this TeraGen job running and these files being ingested, I'm just going to stop the tunnel between the 2 data centers. So they are indeed separated. I'll just do a quick proof point of that. If I try to SSH to my Oregon data center from my North Virginia data center, you'll see that the SSH window simply hangs here. So I've shut the tunnel between the 2, but you'll notice that the jobs keep running. Once I start the tunnel back up, however, in fact, that job is completed, all files that were basically waiting in transit, that global sequence of events that Jagain talked about, those sequences still were able to achieve a majority quorum despite that network separation for the 2 folders that we were ingesting to. So the system will automatically work out any updates to those sequences. Everybody will play back. That's the catch-up that Jigane showed you a little bit earlier in the sort of pseudo animation on the screen. And now that we've kind of got this going on and we've interacted with the system, how would an administrator kind of look at the audit trail? How do we know what's actually gone on inside the system? Well, the way we can do that is we can come to the Fusion dashboard, and we know that we were replicating into our data center 2 location. I just lose my network here. We know that we were replicating into the data center 2 location, so what we can do is we can simply take a look at the file transfers. And we can look at a list of those files that are complete, that are in progress, or otherwise. Now, even if a system like this one decides not to respond, because the system is completely consistent, we still have replication between the 2 sites. So none of the actual file data was ever actually lost. Also, we can look in the alternate direction. So if we look at, say, the REPL2 folder, and we look at a list of file transfers, again, we can see which files are in progress. We can see the start time of each of those folders, what the total time was, what's the size of the file that was transferred, and how much of that's remaining. And of course, we can look at each one of the files that were complete. So from an audit standpoint, we get a sense of exactly what went on at any moment in time. This has been particularly of interest to financial institutions, again, any regulated industry who has to be able to not only prove that they're replicating the data, but be able to prove that it's consistent and that they know exactly what went into each of the locations. So this is essentially how you manage a system that is constantly consistent despite network failures that we introduced into the system. It's a look at WANDisco Fusion. This, of course, this Fusion 6 node is come back online. It's the one that I basically partitioned off a little while ago. But if you take a look and we go back to the file transfers here now, of course, we can see the completed file transfers from our TerraGen as well. So all those have now caught up as well. And that's an active environment for multiple Hadoop clusters across any geographic distance with strong consistency. Questions?
Thanks, Brett. So as you can see, when a network partition or a WAN link goes down, if you have majority quorum, that particular side of your partition continues to be in read-write mode. You can continue doing ingest and other jobs. The sequence of events, the writes that are being made, is stored in that particular side. When the other side comes back up, it looks and says, I've fallen behind in the GSN. I need to catch up. It grabs all those, applies those. Only when they're caught up, it'll go into read-write mode. That keeps the data consistent. There's no question of one side making conflicting changes, and you have the ability to do active-active ingest architectures with the system. Let me open it up for questions. Yes?
Yeah, sorry, I joined in the middle of the session. So what I understand that you are a strongly consistent system and it's a distributed storage environment.
Correct.
So, so I'm just trying to understand. So are you compromising on availability or partition failures?
So if you're referring to the traditional CAP theorem, what is happening is that the side which has majority quorum is in read-write mode during the partition. The other side, it can't get majority quorum, so it will be in read-only mode. When you have the link restored, we apply the changes that were made by the side that's in read-write mode, and then when the systems have caught up, all of them can be in read-write mode. So that's how it's worked out.
I also noticed in one of the slides that you work with HDFS.
Correct.
So you work with Hadoop compatible file system as well as HDFS?
Yes, we have compatibility with both. And I see from your t-shirt that you perhaps...
They're working with you.
Yes, we have tested with your environment and it's fully certified at this point.
Yes.
Two questions. First of all, if you had three servers on each side and you had a partition, what would happen then? Nobody would break it because there's no quorum?
So
there is, yeah.
Go ahead.
We'll fight it out. The quorum engine is configurable. Interestingly enough, when you have an even number of nodes, assuming that you're letting all of them participate in a single quorum engine, we give one of them, in Paxos terminology, called a distinguished node. So it effectively, the easiest way to think of it, while this would be an incorrect way to say it, is it gets an extra vote. But it basically has a little bit more weight to the agreement engine so that you are effectively creating an odd quorum with an even number of machines, which means that the site with the distinguished node would have favor over the site that didn't. So that would be the one that was still writable.
But if you had then 2 and 1, and you had a partition, and one server went down,
So if
You wouldn't.
then you would have no rights.
I mean, you wouldn't be able to get a majority. If you, I mean, you can conjure up a system which has exactly 3 and 3, and if there were a partition, you wouldn't get majority quorum in that case, and both would have to stall. But our interfaces will not allow you to configure that. And we have administrative capabilities to rotate the quorum through follow the sun type situation. So if you have a Europe data center and a US data center and a Asia data center, and you want to keep the majority quorum during specific hours in the US and then move across the world, we can do that. But effectively, you can cause this to stall if you want to go out of your way and misconfigure it. Yes?
Well, not misconfiguring, it's if you configure it with a quorum, right, and one of those servers goes down, it's supposed to be one of the quorum, and there's a partition at the same time.
Well, that's why we recommend that you have 3 in
Odd
each
number,
location.
yeah.
Right? A minimum
majority
of 3 in each
quorum
location. Each folder that you replicate, I had 3 folders there. I had REPL 1, REPL 2, and REPL 3. Each folder gets its own state machine. So I can give each folder, weight the quorum which way I want it. So I can always guarantee that I'll get quorum at a particular location if it's very important for that location to always write. So I can spread the quorum out for sort of distributed quorum where majority quorum is achieved over multiple data centers, or I can force all 3 of the nodes in a local data center to be the agreement engine. Doesn't mean I can't write from the other locations. All locations would always be able to write, but they'd have to go through that one site for agreement. So it's very tunable so that you can decide performance over functionality and so forth.
One more question. Are you doing this for HBase as well?
So HBase is, there is a little bit of additional logic between the HDFS writes and the HBase API. So there are a couple of ways you could deal with it. You could coordinate before the puts go into the system, or if you were to just treat the files going into HDFS, you have less visibility into HBase application logic. Then you're left with more of a disaster recovery type solution. So it depends on what you want for your particular use case.
Set up the puts to get quorum.
There is a way to do that, not as part of the Fusion product, but that's a possibility. Yes.
So 2 questions. The first one is the consistency is for the metadata of the replicated files, right? If I write a terabyte in one data center, it's going to take some time to
Yes.
go over the WAN. Right? But the metadata of that 1 terabyte that I have written, file sizes, structure, the directory, that's going to be immediately available on the site.
Not quite. I mean, the way we do it is by default on block boundaries, we send out a proposal. So the remote end knows that a file was created and a block was completed. This is for HDFS, which has the notion of block. Other file systems don't have the notion of a block, and you can configure that to say when 16 megabytes is completed, send the notification over. But basically, we're a client on this side and we're a client on that side. So when data becomes visible to the client in the source or the ingest cluster, we have the ability to send out. So if you call hflush, we know, we trap that, we send out a proposal. When the hflush goes down, we pull that data over. So it would be as if the write is happening on the remote cluster. A client seeing that on the remote would see the file created, it would see 16 megs, it would see 32 megs, it would see bigger and bigger sizes. So if you're running a Hive query, and the ingest is not complete, but you're running the Hive, you get incomplete results on the data center of ingest. Exactly same thing happens in the data center that's being replicated too. You get incomplete results. We have REST APIs and we have alerting mechanisms if you want to spin off workflows after the replication is complete. On a replicated folder basis, you can know when there's no data that's not replicated, and you can spin off.
But you see the metadata structure on the other side.
You see the file, and you see the size that's replicated closest to that block that we're using for transfer,
So
but you don't see any more.
You'll see things like permissions, if you change ownership, that's
All of
synchronized.
those, yeah. All of those are coordinated.
We'll coordinate things like file opens. So if he opens the file in data center 1, then me sitting in data center 2, if I try to append to it, I couldn't. It would be file already open for write. So when we'll coordinate the file close such that when all the data finally finishes streaming, file close will get coordinated, and then I can write to it again, assuming nobody else has opened it up again.
And the second question is, given that you are in the data path now, what is sort of the performance over it? Because this consensus is synchronous.
So we're not in the data, but we watch the data going by, but we're not in the data path. In other words, what actually happens is we have a client jar that's loaded, and if you use the Fusion URI, we get the request to write, but we pass on. We use a Fusion output stream, but it's just a pass through to the output stream below us, which could be HDFS, and it's the pipeline. So we count the bytes as they flow by, but we don't do anything to the bytes. We don't store them. It's just a pass through, and it's all in the same Java VM. So there's no performance impact because we're not coordinating the data transfer. We're just coordinating, 128 megabyte boundaries.
So you're in the metadata part.
We're in the metadata path. That's
so
correct.
What is the overhead for, like, if I'm doing a metadata workload that is just like creating a bunch of files?
If you're creating a bunch of files of 1 byte size, metadata operations are going to outweigh the data operations. So our Paxos is pretty intelligent. We have the notion of batching, where you can batch a number of operations from all the clients connected to one Fusion server into one agreement. That mitigates, so you lose on latency, but you get better throughput. So you may get 1,000 metadata operations synchronized by one Paxos transaction. So you pay the cost of that Paxos transaction over all of those. That would be the mitigation factor for that. Although its normal use case in HDFS is larger files, and metadata operations are a small fraction of that. Yes. Okay.
How do you manage massive deletes?
Massive deletes are a metadata operation. If they go file by file, batching is where you'd get your performance back. There's a little bit of trade-off. You're going to trade off latency for throughput, but if you have 1,000 deletes that are going by, that will get coordinated with one Paxos transaction, and that's how you keep the performance up.
What if you have 14,000 or 20,000 deletes going through at the same time?
20,000 deletes going to this. I mean, it's going to be a question of batching, right? At that point, whatever, if you have a 200 millisecond latency to the other data center clean across the world, and Paxos mathematically is 2.5 round trips before you can get an agreement. And that's just math. You can't make compromises on that without compromising the algorithm. So that's 500 milliseconds. So all the deletes that came to us in a 500 millisecond period may get coordinated with one Paxos transaction. That's how you're trading latency, because the delete that you started at millisecond 1 and the delete that you started at millisecond 499 are all going to be batched into one and sent out. We call that boxcars, but effectively in a big data system, you will not see any performance differential because of techniques like this.
One question. You said you would send data block writes, right? At the end of the block boundaries.
That's a configurable option. By default, it sends at block boundaries, but you can configure it to as low as 16 megabytes.
Is it because that you want to make sure that the primary would get returned the block so that the other side would have the block, and if there's any problems that you'll be able to stop?
It's more to keep the WAN fully occupied. We have WAN bandwidth management capabilities, so you tell us that you want to use 800 megabits out of a gigabit for this replication. We want to keep that fully occupied. The problem with solutions like DiskCP is that it starts up in an hour and it wants 10 gigabits per second because it's a spiky workload. We want to keep your bandwidth fully utilized. So you give us 800 megabits, once 16 megs or 32 megs or block boundary crosses, we want to start transferring that file. So we don't have a backlog of too much data to be transferred. That's why we do it that way.
And also, if there's any failure on the block boundary return onto the primary, for example, or say this sort of space, you would make sure that the replication doesn't happen on the other side.
If there's a failure, we would get all the data up to the failure point, and we'll transfer that over. But the client is writing in the data center of origin. So if it fails at that point, there is a partially complete file. We'll truly and accurately replicate that, but you've got a partially written file on both sides now.
Do you support?
So Konstantin Shvachko, our chief architect for big data, is the original author of the name node. Our HDFS knowledge comes from that fountainhead, if you will. He's a big open source proponent, and we're working with the open source community to open source parts of this technology, yes.
So S3 and MapRFS are also...
We are compatible with S3 and with MapRFS, yes. And you can go from MapRFS to HDFS to S3 completely seamlessly.
So this, sorry.
How does your quorum mechanism compare to like something like
ZAB is more of a leader-elect and then process. Our system is truly no leader, so every transaction has a voting mechanism as part of that. The quorum gets applied to every transaction.
And ZAB is not WAN capable. You're limited.
Because of various...
They're restricted within data center.
So I think pretty much, if I understand correctly, like you were answering somebody else about HBase. So right now, it's much more compatible with all the file systems.
It's a file system replication technology. It's compatible with about 90-95% of the applications, I would say. If you want truly active HBase, then Paxos has to be applied at a higher level. And there are ways to... We have products that do that in a different stage of development, but that's true.
Do you have any limitation on speed of replication?
So this is the interesting thing, right? I mean, I used to work for Eric 14, who was one of the motivating people behind DistCP. And the focus was always on scaling DistCP. But my perspective is different. You need to scale the replication to the size of the WAN bandwidth. So if you've got 10 gigabits per second, that's what you need to scale your replication server to. You can have 3 servers, Fusion servers, and load balance across those for replicating 10 gigabits per second. But if you've got a 1 megabit or a 1 gigabit link, a single Fusion server it'll be sitting at 10% CPU utilization. It's very underutilized.
Follow-on question to that, then the opportunity for quality of service.
We have WAN bandwidth management at this point, and you can specify that a specific replicated folder has higher priority, and you can specify the number of megabits per second for that. That's a level of quality of service we offer as part of our product. All right. Thanks, folks. Thank you for coming. Appreciate it.